The Çanakkale Strait leads to the port of Istanbul in Turkey. As the gateway to two continents, it's one of the most important waterways in the world.
You have Europe on the western side and Asia on the eastern side.
It's also one of the narrowest straits in the world, making it crowded and hazardous. Winds are funneled down the channel, which is also situated in an active earthquake zone. All in all, it's not the easiest place to build a bridge. But here, stretching over 2 kilometers, is the longest suspension bridge on Earth.
I mean, the suspension bridge is the only solution that will take you on such a long main span.
Completed in 2022, the 1915 Çanakkale Bridge is a symbol of triumph against the forces of nature and other great adversaries. Its name commemorates the Ottoman victory in the infamous Gallipoli campaign, which centered around this waterway, also known as the Dardanelles. The towers at 318 meters mark the date the Allied fleet launched their failed naval assault. Its length, 2,023 meters, celebrates the 100-year anniversary of the Republic of Turkey.
And then if you look at the anchor blocks, this is what ties the cables to the rest of the world, are shaped almost like the Trojan horse. So there are lots of symbolism built into this, and that's a part of it, I suppose. But also, for a bridge engineer, it allowed us to take technology and design to new limits, new levels, and we like that.
But pushing the limits brings risks, especially when it comes to suspension bridges and wind. So, for the record-breaking Çanakkale Bridge, engineers settled on an innovative design that breaks with tradition: the twin box girder. A box girder is like a hollow box, made of steel or pre-stressed concrete, a design which helps make the deck rigid. But the Çanakkale Bridge splits this shape in two, introducing a large gap down the middle.
In case of the Çanakkale Bridge, 9 meters.
It makes the bridge wider and more expensive.
You need more material, you need some cross beams to go in between.
But it's also far more stable, preventing the kinds of dangerous vortices that tore apart the Tacoma Narrows Bridge.
Now, in order to understand why and what the gap in between the two roadway girders does, I mean, you must envisage a bridge deck like an airplane wing.
Aircraft are able to fly thanks to the shape of their wings, which generates lift by changing airflow. As air travels over the curved upper surface, it sets up a region of lower pressure above the wing compared to below, creating an upward force. But interrupt that airflow with a gap, and the lifting force disappears. The size of the gap is crucial.
It is important. If you make it too short, it doesn't really work. If you make it too long, well, then you would have too much air washing in there, creating vortices, which you don't want.
To work out the optimum width of the gap on the Çanakkale Bridge, engineers needed to test a scale model in a massive wind tunnel, analyzing the full structure at different wind speeds, including the towers, deck, and cables. Movement is inevitable, but to provide the bridge with the appropriate strengths, those movements need to be understood. The twin box girder is an integral part of being able to make a 2-kilometre main span. And with it, engineers can be sure the bridge stands strong in any gale.
And it would simply not have been able to be there had we not done that.
Wind is far from the only danger in the Çanakkale Strait.
And it is quite a long crossing, and there's really extremely much ship traffic passing, because everything going to the Sea of Marmara and going to the Black Sea, and all this ship traffic is passing there. So it is a high ship risk, collision risk area. Like 40-something thousand significant size ships every year. So it's from a shipping perspective, it's quite busy.
So this bridge was designed to survive a collision of the worst kind. In 2024, a tragic example of that danger played out in Baltimore. In the early hours of March 26, the massive container ship Dali suffered a total power failure, causing it to lose all ability to maneuver. With no way to avoid a collision, it slammed into a main pier of the Francis Scott Key Bridge. The collapse was instantaneous. Six construction workers on the bridge were killed, and the port of Baltimore was paralyzed.
Accidents like that are, of course, very tragic. I mean, a number of people died, but it could have been a huge catastrophe had the bridge been full with traffic. And I think the authorities managed actually to close the bridge in a tremendously short time.
With the bridge enmeshed in the Dali and blocking the waterway, one of the US's busiest shipping lanes was shut down at a cost of $15 million a day.
Quite clearly in Baltimore, the protection measures were insufficient for the ships that had begun to navigate that channel.
The bridge was designed with protection measures called dolphins, small circular concrete structures near the pylons.
A dolphin is a bit like a car bumper in a sense. It's a sacrificial element placed away from the bridge structure. It's completely separate structure. It's concrete or timber or steel piles into the seabed with a large concrete top on it. And when a ship impacts a dolphin, the energy absorbed in destroying the dolphin is the energy release that halts the ship's movement.
But the dolphins were built decades ago to protect against ships a fraction of the Dali's size.
So this bridge was living in a changing risk environment, which wasn't clearly fully appreciated.
Ships today carry around 10 times as much cargo and are almost twice as long as they were when the bridge was built. And the consequences of that oversight were enormous.
I mean, you can't just build a bridge under a certain set of assumptions and then just believe that it will be fit for all future purposes.
To remove the ship, the giant twisted bridge sections were cut by welders into smaller pieces and demolished in controlled explosions.